So, welcome back everyone. In the past two lectures, we have been understanding how light can also be considered as a wave in the first lecture, and also we got introduced to Thomas Young, who was a fellow Englishman who performed a greatest scientific experiment that proved that light is also a wave. That was a debate, and in the second lecture we got into detail about knowing how Young performed his experiment of double slit and what all he could derive just from the observations, and also derivations of formulas like the width of the fringe, number of fringes that are of bright, number of fringes. All those derivations are very much important. And now in the third lecture we would be discussing the modified cases of YDSE. So the first thing that we would start with, the first case, is if white light is used. This is a very common one. If white light is used in YDSE, then as we know, the wide Young of the first dark spot is lambda d upon 2d, in which we can say all this is constant, all this part it is constant, so yd1 is directly proportional to lambda. That is the first dark spot. Now let us draw the slits in order to again get understanding better of what we are actually thinking of. So over here is our C, this is our bright one, and over here this is our D1. So with increase in the wavelength, with increase in wavelength, there would be increase in the distance of YD1, that is, it would go further. And one more thing to notice is that if a light ray came in from both the directions, if light ray came in from both the directions, then it would have to travel equal distances to meet at C. So all colors will have same point of maximum or the central bright. So central bright would appear to be white. This is there. And also with increase in lambda, YD1 would increase, so the dark spot would go further, and increase in lambda. So now let us see where the lambda, that is the wavelength, is the strongest. If I write the colors of the rainbow, that is ROYGBIV. So this over here in this side, wavelength increases and frequency decreases. Red has the highest wavelength, that is of around 700 to 800 angstrom, I think, nanometer. 7000 it would be. And okay, I'll not write the little units as there's an ambiguity. And violet has the least, that is of around 400, 450 something. So the red color would be not here closer. So what I mean to say is that red color has the highest lambda, so its dark spot would go up and hence red color would appear up, red family would be up and blue family would be down. And how, if you ask, then it all depends upon lambda. Now we have to calculate with the help of lambda and all the given distances where actually would the distance would YD1, that is the distance of the first dark, be from the central bright or first bright, and then if we took the ratio, take the ratio, then we would get this thing that I have written. And all this is important. Now the second case is if whole apparatus is dipped in a medium of refractive index nu. So it is very easy. The formula for mu is frequency, let us revise it. Lambda of 1 with respect to 2 is C2 by C1, that is equal to lambda 2 upon lambda 1. So if they have given mu, that is equal to lambda in air upon lambda in that medium. So let us take this as 1. So lambda in air becomes lambda 1 upon mu 1. And this is it. We replace this everywhere. And that's it. We get all our formulas back. May that be anyone. For example, let us take this one, this which we worked on right now as an example. So here I would replace lambda. For example, yes, I'll write over here example yd1 equals to lambda d upon 2d, and now I would write it as lambda 1 upon mu 1 times d into 2d. So I replace lambda in air by lambda 1 by mu, and that does not make a difference. That's it. And now we can solve it again. So now let us understand the new concept of optical path. So what an optical path is actually, I put, there's this glass slab having a thickness of T. Okay, so this is our case 1 wherein I'm putting a light ray from here. So now it has a velocity v and a refractive index of mu. So it would travel with v's velocity, which was assuming that mu is greater than 1. So v would be also small, v would be a very small value, and so the speed of light in that medium would reduce, and then again if it comes back the speed would retain. So assuming it took time capital T, I am writing this as time, is equals to x by v, and that is equals to T by v. Now over here this is the thickness. So the light took capital T time to move from this end of the glass slab to this end of the glass slab. And now if I give an ordinary light in vacuum, if I give capital T time, then the distance covered would be x dash, assuming, and so again the velocity would be c, would be displacement per unit time. So from here t would be equals to x dash by c, and x dash can be t into c, but we know capital T is equal to small t by v. From over here I write small t by v times c is x dash, and now this is the distance, x dash is the distance covered in the air, which should be obviously more. If we see, if we give the same amount of time, so let us take an example. If there's a tractor which is moving with the speed, it is trying to move at a constant speed, for example 50 km/h, but it is unable because it is traveling in mud, so it will go at 30 km/h, while the the tractor which is running on a highway can easily reach 50 if both the tractors are same. Then if I give t time for them, let us assume 1 hour, then the second truck that was on the road would travel more distance as compared to that of the one in traveling in mud. So the same is over here. In vacuum there are no obstacles, so it will move faster. So x dash would be greater than x. So path difference delta x will be x dash minus x, which can be written as t by v minus c. Oh, sorry. T by v into c minus t by v. So I take t by v as common, and wait for a minute. We don't have to do this. We have already got the answer. So arranging from here, x dash is equal to t into c by v. So now what is c by v? If we remember, nu is equal to c by v. So I write t times mu is equal to x dash. So now the arrangement would be simplified. So now I write the difference between the part as mu t minus, over here it would be t, as the t distance it had to travel. So mu minus 1 times t is the extra path it had to travel. So now the shift in the central bite rate. This is now where the third case comes in of modification. So now this is our ordinary piece, and I put a glass slab of refractive index mu and thickness t. Let this be S1, let this be S2. And so earlier it had to travel this as over here. This used to be the C, but now the new C has shifted up. Let us assume. No. We'll prove that the C it goes in the direction where the glass slab is put. And now let us see how. I mean, before understanding it mathematically, I'll give you a visual proof of it. So now there's this tractor once again, and both of them have to meet at the same time. The tractor that is running in the mud as well as the one driving on the highway. So for them to meet at the same time, the tractor which is in the mud would cover very small distance in time t, whilst the truck on the highway would cover comparatively larger distance in the same similar time. So for both of them to meet at a certain time, the second one has to travel much more distance. That is, as we can see from this diagram, much more distance has to be traveled, or else both will not meet at the same time. And that means both meeting at the same point, that is delta x equal to 0, is our essential condition. So we equate extra path by S1 is equal to extra path travel by S2. Traveled by S1, that is mu minus 1 into t, that we already derived over here right now. And the extra part traveled by S2 would be d tan theta by putting on a perpendicular. I'll also do that in the diagram, so that let there be no confusion afterward. And let this be theta, let this be theta. Okay. So now I write tan theta as y d by capital D, then mu minus 1 into t. And for y, we shift all the things onto the left side. Mu minus 1 into t upon d equals to y. That's it. So this is the shift in central bright. And if we want to write it in terms of beta, and the formula for beta is lambda d upon small d, and so beta upon lambda can be written as capital D upon small d, which we can see over here in this equation very easily. So we write beta by lambda mu minus 1 t upon lambda d, oh sorry, d also gets replaced, equals to y. So this is another formula for the same. So let us move to one last and the final concept, that is the number of fringes shifted. Number of fringes shifted by central bright. So what this means, let us understand diagrammatically. Just a minute. So it means that here there is this YDSE experiment of ours, and again the standard notations. This is D, this is S1, this is S2, this is capital D, and there is this block of thickness mu, sorry, it's refractive index mu and thickness T. So earlier, if there would have been no block, then the central bright would have been formed over here at its position. But now that there has been a slab, so the fringe would shift in the direction of the slab. Let us assume over here and in this distance there have been a number of slabs which they are asking. So let us consider this distance as y, this point is p. So how will we do that? So we know the formula for shift, that is this y that we have derived, which we can use now. So it is mu minus 1 t capital D by small d is equal to n times the fringe width beta, and the fringe width beta is equals to lambda d by d, capital D by small d is equal to capital D upon small d, thickness mu minus 1. And so we cut these terms, and for n we keep it on the right side, we send the remaining terms on the left, that is only one term, lambda upon lambda, and this gives us the number of fringes in between. Now that includes the bright fringes as well as the dark fringes, and that is it. And we have now completed officially with the part of wave optics on Young's double slit experiment. And one last thing before we go that I have to discuss is, that's not that important, we can derive, but still it's good to discuss it. If in certain field of view n1 fringes are seen, are produced when lambda 1 wavelength is used and n2 when lambda 2 is used. So I can write it as n1 when lambda 1 and when lambda 2. Then we can write n1 beta 1 as y. The y is the distance from C, and we can equate it as n2 beta 2 equals to I. So n1 beta 1 equals to n2 beta 2, and yes, we are expanding n1 lambda 1 d by d equals to n2 lambda 2 d by d. This 2 cuts, and n1 lambda 1 equals to n2 lambda 2. That means we can say n times beta is constant and n times lambda is constant. These two things are also frequent type of questions. And with that, we have now covered with almost all the part of the Young's double slit experiment. Thank you for watching.